So today we welcome Lorenzo Contessi, who is a postdoc at IJCLab in theoretical nuclear physics. So he did his PhD at the University of Trento, and then he did a couple of postdocs in Israel, CA, and IJCLab. And mainly his work is on nuclear physics, many-body systems, as well as effective field theory, which we'll be talking about today. So the stage is yours, Lorenzo.
Thanks a lot. Thanks a lot for the introduction, and welcome to everyone. So thanks also for the opportunity to be here and talk a little bit about effective field theories, ab initio methods. I know as theoretician is always here to talk in the sense that you always have the urge to show many equations, but I will try to give a rough idea of what we are doing, why we are doing what we are doing, and especially to give you some something to take home without being too technical. But okay, some Lagrangian might show up. I will tell you when the danger is near. So, okay. So the context of what we are talking about is ab initio. So ab initio in let's say in the definition of in the context of effective nuclear physics means try to describe nuclear phenomena starting from nucleonic degrees of freedom. So you want to use proton and neutrons describe the interaction that is between protons and neutrons. This is not the only way you can describe the nuclear chart, but the idea is that if you know this interaction, you have a lot of flexibility to describe many phenomena, and you want to increase the predictive power of your theory such that you can describe as many things as you can with the least initial information as you can. And there are two problems. Let's say there are two challenges in ab initio techniques. One is knowing the interaction, because you need to know what is the interaction between nucleons, and the other one is to know how to get information out of this interaction. So usually this is done using solving the non-relativistic Schrödinger equation. So you need to solve this equation, the Schrödinger equation, but the problem is that solving this equation is hard, because if you have many particles, you have many degrees of freedom, you have high dimensionality, so you need usually a strong computer, a strong method to solve this equation and to get what are the energies, the wave functions. So two problems, the interaction and the method. Now, I know that in the title, I wrote ab initio methods as well. I will focus more on the interaction, especially because there was a nice talk, well, a few nice talk about this, one of which is from Thomas Duguet, and I suggest you to go back to this colloquium. I'm sorry that I stole one of his slides. I hope this is not bad, but it's for propaganda purposes. So this figure was actually from Benjamin, which is also in the audience. So I'm sorry if I got this, but I think it represents very well how much the ab initio method improved in the last years, because ab initio methods are hard and the many-body Schrödinger equation is very difficult to be solved. But in the last years, we had huge improvement, and now we can tackle even very large nuclei with 15 particles from ab initio techniques. And I think this is outstanding. But this is only half of the story, because if you have a method, you need also to have a theory that can give you results with comparable precision. Always is the interaction that you have and the methods how to solve the Schrödinger equation. Now, I want to talk about this interaction. Now, of course, there are different ways of looking at the nuclear physics problem. One would say that an ab initio approach, so an approach that is really fundamental, should be from quantum chromodynamics or even string theory. The problem is that quantum chromodynamics is not easy to be solved for many particle systems, because quantum chromodynamics becomes non-perturbative in the nuclear physics regime. This means that when you solve the quantum chromodynamic theory and you try to get observables, you need to take into account, in principle, infinite gluons, quarks. Is very complicated, and it is possible to do something like that using lattice quantum chromodynamics, which is a kind of calculation, but is extremely expensive, and this is not feasible yet. But this is a completely different story. So people prefer to start with a more, say, low energy degrees of freedom, which are nucleons, and maybe include mesons, light mesons. So nucleons can exchange mesons with each other, which is the long-range part of the interaction. And then, of course, they can interact when they touch each other because the quarks inside the nucleons can interact with each other. And this means that they have a contact part, the interaction, and then a meson exchange. But then if you decrease the range of momentum to which you are interested, you can also integrate these pions inside the nucleonic degrees of freedom, and somehow you essentially have just a contact interaction, an effective contact interaction. This is the contact theory for nucleons, or pionless effective field theory. If you talk about effective field theory, I will go back on the effective field theory in a moment. And this is, I say, a low energy representation, or a low energy way of having nuclear interaction than the chiral effective field theory that uses pions as well. And of course, you can change the degrees of freedom. For example, you might be interested in a cluster, a more cluster approach. So you have to define a interaction between cluster of nucleons. If you have a clusterization in your system, this might help you and reduce the number of degrees of freedom. Or even you might think that your degrees of freedom now is the density, and you might have a theory, as a function of the density of the system. And the problem here is very difficult to make an effective field theory out of density. And again, this is another very interesting point, but for another time. Okay, as I said, I'm working mainly with effective field theory. This means that when I look at the theoretical problem, I intrinsically think on effective field theory, but this has not always been the case in nuclear physics. In fact, the first interaction that we have in nuclear physics are more phenomenological kind of models. Phenomenological kind of models means that you have a good idea about the physics of what's happening, and if you have a successful model, this is a simple theory, or as simple as you can, that can describe well what's happening in your system. Means that you can have a relatively precise model that gives good results, that should not be too complicated to be understood, and can describe physics from simple as concepts. And we have many different kind of interaction that come with different ideas and different forms. For example, the famous Paris interaction. You have AV4, AV4 prime, all the argon interactions, CD bond, all those are models. The problem of the models is that they intrinsically are connected with the idea of the physics that you are trying to understand. And in fact, once you have this model, it's very hard to improve it, because essentially the models gives you the physics that you are trying to describe. They are interconnected. So it's hard to see how precise will be your model a priori. You don't know really what you are missing out, because it's not there from the first principle. And then it's difficult to improve the model in a simple way. Well, there are ways of doing that, but it's not as straightforward. So this is one of the reasons why people started to work with effective field theories. Effective field theories are theories that have another concept. They start from a different philosophy. So your interaction is not a priori. So you don't try to describe your interaction from a priori principles. You have symmetries of the fundamental theory. And from that, you try to build an interaction with some kind of expansion, improving that in orders. So you can include more operators in your interaction, in your potential. And every time that you include a certain amount of operator, you can say, okay, my theory has increases his precision, describes better physics, and I have a theoretical error estimation order by order, and I know how to improve it. So it's a way of improving the theory. Now, this is the hard part. So I warn you, there will be some Lagrangian. I will try to pass fastest through diagrams that are easier because they are pictures. But the idea is that you have a Lagrangian. So this is just the only hard part. So you have a Lagrangian that is the underlying Lagrangian, if this makes sense, and you don't know what it is. So essentially, you try to expand this Lagrangian in orders. In this case, you try to expand it in a Taylor series in the momentum of your particles. You do this because essentially you try to describe the low energy behavior, also the low momentum behavior of your systems. So you think that having this momentum expansion will converge, and higher orders, so higher power of the momentum, will be smaller, will contribute less than low power of the momentum. So in principle, you have the kinetic part, that is the one that has the lowest momentum. Then you have two-body interaction. Notice that those are fermion field. The fermion field carry a 3½ dimension. So every time that you increase a number of fields that you have in your Lagrangian, you have a 3½ and 3 also. Essentially, you have 3 powers more. So this is a two-body interaction. And then you have a 3-body interaction, which is a power of 3 more, and so on and so forth. And then you order all these interaction. If physics would be like this, that would be very trivial or boring. And in fact, in physics, we have fine-tunings. So we know that the two-body interaction is not less important than the kinetic part, because deuteron, for example, has bound states. We know deuteron is bound, so the potential interaction should be at least of the same order as the kinetic part if you want to describe this bound state of deuterium. So there are many of these different things, and here theoreticians enter in the work. This is not trivial, but essentially, let's take this as a black box, a magic black box for which theoreticians, okay, those are the diagrams. Theoretician tells you, okay, now at leading order, you have the kinetic part, mass, of course, and then you have three-body interaction. Then you have the next order will be another two-body term. This is momentum dependent. You will have 4-body, and so on and so forth. And now this is only the contact effective field theory powers. So these are power counting for contact effective field theories in nuclear physics. But this is not the only effective field theory, of course. But it is simple. So I usually work and just try to explain these things using the contact one, because is a simple power counting. And the point is that those are powers of some parameter that is an expansion parameter of your theory that is supposed to be smaller than 1 for the system you are interested. So if you are interested of just the leading order, you go here and then you can refine it, and you just have to add these diagrams that actually are Hamiltonian pieces. And those Hamiltonian pieces you can include one after the other. They are smaller and smaller. This means that you can include them in perturbation theory, and actually you have to include in perturbation theory. I will go back in that in a moment. But essentially, you can improve your theory and get observable with an error as much as you want, including enough operators. When you do the calculation, actually, you don't work with a Lagrangian. You want to have really a potential. This is because you are trying to use many body methods. When you are dealing with 2, 3, or even 4-body, maybe it's different. But if you want to solve the Schrödinger equation, you need to have a Lagrangian, an Hamiltonian. So you transform all your contact interactions that you had before in a Hamiltonian, and then those are contacts. So they are power of momentum and 2- and 3-body interactions. But this is not, they cannot be directly used in a many-body code. What people do is that you transform those in something that is not really a contact. So instead of being just one here, they become mirrored. Those are mirrored contact interactions. You can choose the form. Here I choose a Gaussian, but there are many other ways of doing that. In principle, you can also not use a cutoff regularization. You can use something different, but this is the simple way for many body purposes. And essentially, you say, okay, when this cutoff is large enough, they go back to be a contact interaction. And when they are a contact interaction, only there I can have this count in power of the momentum. It's very important that you are able to map back to the contact limit using a cutoff that is large enough. However, not all the theory are, not all the theories, this is simple. In fact, for example, there is the chiral effective field theory. There is the Weinberg power counting, okay, of chiral effective field theory, which is the most widely used, I would say, is chiral effective field theory you see everywhere. It has exactly this kind of problem. You cannot really go to the contact limit. Now, the contact is not really the contact just for 2 nucleons. It is the contact including pion degrees of freedom. So nucleon, pion, and nucleon. So the contact contains all of this. But the point is that if you want to have power count in terms of power of the momentum, you need to go to the contact. But if you try to do that, for example, here is the energy of helium-4 on this paper here, you see that the leading order starts to converge, goes actually very close to the physical experimental point, but then suddenly there is a jump. And then you start to ask, okay, what is the point that I have taken from where I should start to count the error of my theory for the leading order and this expression? One would say, okay, it's the largest cutoff you can take, and this is here, but probably was better to stay in this region of cutoff, and that's why many people are tempted to just fit the cutoff, the best cutoff that you can get to reproduce the physics. But if you do this, you are not anymore in the content limit, so you lose the power counting and the error control of your theory. Of course, there are ways of restoring error control. One of these is, for example, using Bayesian analysis. And I would say this is a great method. You just have to have let's say a meta-analysis of all the interaction that you can have with a certain cutoff range. And then you see how much different regularization, different cutoff changes your prediction for the observable that you have to your disposal. But of course, it is hard and expensive. So in principle, you would like to be back to have a priori error control. So in 2021, Changji and others published a version of chiral effective field theory that looked to solve this problem. In fact, you see that the leading order is the red band and the next leading order is the blue band. And this looks to be more control in the sense of the cutoff. So you can essentially try to extrapolate to the infinite cutoff limit. And this looks to be much better than before. Of course, there are still some controversial, but I would say it's a step towards having error control in the chiral power counting. It is called modified chiral power counting by them. But this power counting got a problem. And the problem is that when they try to go to oxygen, so they try to use this power counting to capitalize on this interaction. They went to the many-body system. They tried to calculate the structure of oxygen-16. And what they found out is oxygen-16 energy was less, the binding energy was less than the closest threshold, which is the 4-alpha threshold, meaning that the leading order of this interaction tend to break oxygen in the 4-alpha particles. So we know that oxygen is not very far from the 4-alpha threshold, and probably this is just a small correction in terms of energy. So it's not necessarily that this is bad in terms of the theory, but essentially what they find out that the leading order was not stabilizing oxygen. And this is pretty bad. Okay, it's not always. For small cutoff, they find stabilization, but then when the cutoff increases, you see this oxygen becomes less energetic than in magnitude than the 4-alpha threshold. Now, in the paper here, they propose to add a 3-body force, which solves the problem. This is a possibility. Another possibility is that you don't change the power counting, so you don't add a 3-body force, a leading order. You treat subleading contribution in perturbation theory starting from a state that is not stable and try to stabilize it. Now, this is a theoretical problem. It's not trivial. There was a paper by Changji in 2023, which says this is possible, but brings many problems. But this would have the advantage of not changing the power counting. So essentially, you don't add other terms at the leading order, making the leading order more complicated. So there is another theory in which this happened. So the instability problem happened also for pineless theory, which is a simpler theory. It's not a chiral theory. It's a theory for lower momentum. I talked about this before. It's only contact theory. And essentially, this is the theory I started to work with in Trento when I was PhD, and then I continue to work, because essentially this is very simple to understand that there is no pions. The theory, of course, works for lower momenta, but the limitation of this theory is relatively understandable. And this means that you know where this should work, is expandable, and actually works not only in nuclear physics, it's a contact theory, so it's pretty general and universal. So you can study what is the behavior of this theory in many different systems. And this is very important. I will go back in this in a moment. But don't mistake this for triviality, because it's true that the theory in itself is simpler than a meson exchange theory, but the calculation can be very hard. In fact, the many-body problem becomes harder and harder if your interaction becomes stiffer and stiffer, and a large cutoff means stiff interactions. So this means that if you want to try and test your theory close to the contact limit, again, if you remember where you can actually count what is the typical error of your theory, you need to do very difficult calculations. So this is one of the problems of doing many-body calculation with this kind of renormalizable theory, which you can increase the cutoff, because if you want to increase the cutoff, calculation becomes hard. Okay, I think I still have quite some time to make some marketing. So what I would like to convince you is that pionless effective field theory is not so terrible, even if it is a low energy representation of the chiral theory. So the first observable that you can calculate in pionless effective field theory is the deuterium binding energy, because essentially you can fit the theory to the scattering length of the two body and the effective range at next leading order. So this is essentially a consistency check, but essentially this works well and tells you what you would expect for any observable. So the leading order here, I extracted this from this paper, is the two-body binding energy as a function of the cutoff. Now the cutoff you can push to infinity, or not to infinity. Infinity is never possible, but to as large as you want, because it's a two-body calculation, which is actually solvable analytically. And you see that when you use a two-body technique, so numerically, you're really close to the analytical results, and this is the behavior of the cutoff that you get. So this is a 1 over the cutoff behavior. You always have some cutoff dependence, but this cutoff dependence can be removed by extrapolating the results to the infinite cutoff limit. When you go to the next leading order, in this case, you treat the next leading order as a small perturbation. So you can use perturbation theory. And if you do that, which is relatively simple for bound state, again, you have some improvement. He's not going to the physical value, which is the black line, but you get a good improvement, and then you expect that the N2LO gets a little bit better and better and better and better. Of course, you can do the same with the phase shift, and essentially you see that the leading order phase shift somehow at a certain point becomes far from the physical one, but this doesn't mean that your theory is failing. Actually, when you go to the next leading order, you get much better the phase shift, and then it starts to converge to the physical value. This is what you would expect. The leading order not necessarily works perfectly, but then you can improve the theory order by order. So we did a calculation for helium-4. This is from, actually this was a different paper. This was a paper in about hypernuclei, but we calculated helium-4 because we needed it. And I think this also shows what you would expect for helium-4. So those black points are calculation done in a few body methods. So those are pretty precise. The errors of this calculation are inside the dots. And this is the binding energy of helium-4 as a function of the cutoff. So going on the right is the contact limit, where you really have control over the errors of your theory. And again, this is 1 over lambda extrapolation, and the extrapolated result is this gray band. This is only numerical error, so there is not still the truncation error, but already the central value of this theory is already very well in agreement with experimental data, which is interesting because this theory at leading order is not necessarily working extremely well. So in principle, even if you would have been very far, well, relatively far, that would not be a problem. But in helium-4, it works extremely good, better than you would have expected. And then there are some calculations about, for example, here there is neutron scattering in different channels from Schaffer and Bazak 2023. And for example, here neutron triton. And here I would say that in this plot, you see something that is pretty interesting. The leading order of the theory of violence, it is a scattering calculation, is pretty far with a huge error band. But already the next leading order is pretty precise and in agreement with other models and experiments. And if you look at that, you can see, for example, here that you have a chiral effective field theory and free LO calculation that is here, and you see that the error bands are not much smaller than the NLO less effective field theory. This is because essentially here you have quite a variation between different cutoff because it's not strictly normalizable. While here the errors comes, well, part of is numeric, but the other one is, of course, the truncation error of the theory, which we would say is still dominating. But it doesn't perform badly. So pilot effective field theory, at least for the few body sector, looks to be quite a good alternative to other methods, despite the theory is, first of all, pretty easy and works for low momentum. But I would say this is a low momentum system. We have also calculation for the 1+4 for a paper of Bagnarol 2023, in which they calculate neutron helium-4. Then, okay, we did also a calculation for a resonance. This is a calculation, okay, I should talk a little bit about this. This is a calculation about hydrogen-4 1 minus resonance. So hydrogen-4 is pretty interesting system that have few resonances and numerical methods. So theoretical calculation and experiment are a little bit in disagreement where the position of this pole is, and there are some motivation of that, but this is again another story. But it was interesting to see if a theory that is as simple as leading order pilot effective field theory could find this kind of resonance. So we try to do this calculation, and actually what we find out is we find a resonance, and inside the truncation error of this of the leading order of the theory, we are actually pretty good in agreement with the other calculation from their numerical calculation, for example, Chiron and Frielo. So that was quite interesting because this is essentially a P-wave system, because this is a 1 minus resonance, so it's a deuterium plus 2 neutrons. Or a triton neutron resonance, actually. So this was quite good. And okay, the errors of the leading order theory are, but the resonance exists and they are not very far from other models. This is actually pretty interesting, and I would say that this gives the theory. You would like to continue and see what else you can do. So if you calculate the typical momentum of systems and you go to helium-4, you see that the typical momentum of helium-4 is pretty large. Helium-4 is actually pretty bound. So you would not expect pilots to work as well as it does. But if helium-4 works well, then you would expect that for larger nuclei, the theory should also perform relatively well. Of course, if you increase the number of nucleons, for example, oxygen-16, typically momentum inside oxygen-16 using this formula is larger than in helium-4, but it's not drastically larger. So the theory should perform worse, but you would not expect it to break suddenly. So this is one of the motivations why you would like to use this theory to go to larger systems. And now this comes again. We skip the numbers. It's more interesting to see the plot. And here you see the problem that I showed you at the beginning of this section, which was also the problem of my PhD that made me struggle during my first years. If you use a small cut of oxygen-16 in pilot effective field theory at leading order, it turns out to be exactly what you would expect. So a nucleus that is stable, and the wave function, or in this case, this the density calculated with Monte Carlo methods, looks just like a blob. But when you increase the cutoff, so you go closer to the contact limit where you can calculate everything and everything is fine, you see that oxygen-16 breaks in 4 different clusters, which are 4 alpha particles. Now, this is a projection over one particular configuration of walkers in the Monte Carlo. Of course, these 4 alpha cluster will maintain correct angular momentum, so they will be spherical, but those are the correlation between the particles. And you see that the density clearly breaks in the 4 clusters. And you can calculate different P-wave systems like helium-5, helium-6, lithium-7, beryllium-8 without Coulomb, even calcium-40. And you can see that in all these systems, when you increase the cutoff, those systems tends to break in their S-wave components. And this is essentially a problem for pionless at leading order. And this is the same problem that is seen in oxygen 16 for the modified chiral interaction. Okay. So I probably need to conclude a little bit this session. And the point is that now we face a problem in theoretical interactions. Now we have a good understanding on how effective field theory should work, and we know why we want to use them. Error control, improvability are very nice things to have when you, for example, compare theoretical results with experiments, or if you want to use nuclear prediction for other kind of studies like beyond standard model or astrophysics. But the kind of theories that we have now are either non-renormalizable, so you have to fix the cutoff and you lose a little bit of the control over the errors if you don't do Bayesian analysis, or you have the problem that the leading order doesn't work very well and you have the instability problem. So the question is how to include either something more in the leading order of this interaction, so how to change the theory at all, or how to include subleading contribution in something that is non-stable, but you have to make it stable using perturbation theory such that everything works again. Now, this is, I would say, the part that is more propagandistic in the sense that this is more what we are doing right now. And this is the improved action method. There is a method that we borrowed from lattice quantum field theory. So this is a method that has been used for different purpose and actually in a different way. But that can help in for our problem. And this is the work that we have done, or we are doing actually. There is a lot of work to do with Bira van Kolk and Martin Scheffer and Manuel Pavon Valderrama here at IJCLab. And it actually tries to add, to modify how we define our effective field theory, how we use our effective field theory to solve the problem of having a leading order that doesn't satisfy us. And in particular, I want to start with a theory that is renormalizable, but have the instability problem, and try to get around, so tame the instability problem in a smart way that helps me also in doing calculation. So I said before that when you go to very stiff interaction, you have problems of numerics. I would like also to try to solve this problem, or at least to make it easier. So the first things you can think is, why don't just add next to leading order, non-perturbatively? That's the easiest part. Just add some other things that you think will solve the problem, and just add them in your Schrödinger equation. Unfortunately, this is not really possible, because you will have the same exact problem as the non-renormalizable power counting, in which you cannot increase the cutoff, or you have strong cutoff dependence. Actually, in this case, you cannot even fit the theory for large cutoff, because you have what is called the Wigner bound. And so the range of the interaction cannot be smaller, so you cannot go to the content limit. Exactly, you cannot increase as much as you want the cutoff. And as again, this is a problem, because only when you go to the content limit, you retrieve the power counting in terms of momenta. But this has been done actually in 2018. And for small cutoffs, so where this is possible, it looks like that oxygen becomes stable, and you can essentially get some result out of this theory, even if when you have a finite cutoff, then you can choose this model. But essentially, this also gives you the idea is that when you are including subleading contribution, you can solve the problem, in the sense that the subleading contribution can be the key of getting stability and getting around the stability problem. What you can do is not including just the next leading order. The problem of the next leading order is that this is a contact interaction as well, because everything is a contact interaction. So if you add something that is a contact interaction, this is singular. And when you are including something singular to your Schrödinger equation, you enter in a very dangerous situation in which you might break renormalizability. And again, all the story as before. But what you can do is to add something that is a sum of many subleading contributions such that this is a non-singular interaction. So this non-singular interaction should be small, should be perturbative. You should be able to treat this interaction in perturbation theory because this is made only by subleading contribution. And since it's non-singular, it doesn't matter if you treat that in perturbation theory as you should because it's small, or non-perturbatively because it's non-singular. So perturbation theory and non-perturbatively at the end should be the same once you include all the order of perturbation theory. So this is the idea. Very simple. Just add something that comes from subleading orders and solves your problem. Now, this is, of course, making a mess in the subleading orders, because when you are including something that comes from subleading, everything that is in the subleading orders will change, because if here you are including some percentage of the next leading order, then the next leading order should correct for this percentage. So the effect of this potential, this auxiliary potential, this fake interaction that you are including artificially, should be compensated at each order of the interaction. Because at each order of the interaction, you essentially want to go back to your Taylor series in momenta and have error control and power counting control. So essentially, the next leading order will have some information about this potential. But then which kind of potential you are including there is up to you. So this is pretty arbitrary. And in fact, one of the possible way of doing that is that instead of using a contact interaction leading order, you use a finite range interaction leading order. Now, okay, here I should put that this is essentially a finite range interaction minus the vertex, and this is very small. But essentially, you can imagine that if the range of the interaction that is given by 1 over rho, in this case, is very small, okay, rho is large, this is pretty close to a contact interaction itself. And the difference between these when rho is big and the original interaction is perturbative and small. Moreover, this is a non-singular interaction. But of course, when you include a finite rho, next leading order will know that you are including some part of it by the fact that you are including this range rho. Again, this range is arbitrary. It has no physical meaning, can be whatever you like. But in principle, it will be corrected. So now, there's many studies that use a finite range interaction leading order, but in this case, we have a prescription to remove these finite corrections, so this spurious term that you are including order by order, and then you restore at each order what is the correct errors and power counting. So we are not changing anything on our theory, we just are including something, a leading order that makes the life simpler. Why you want to do that? You want to do that because there is a certain range of the interaction for which we saw oxygen to be stable. And then we want a way to remove this range next to leading order. Now, there are different advantages of this. As I said, the first thing is that when you include this kind of range, it's not the only way of doing that. It's just a handy one just for this presentation, just to not show all possible possibilities, because actually there are pretty other nice cases. The improved leading order will work better, we hope, because we hope that it will stabilize the theory. And since this interaction is larger range, at least a leading order, this means that you can solve the Schrödinger equation much easier, meaning that the many-body method will work better and will be less expensive. And this means that you can do larger calculation with larger nuclei. And then the next leading order, of course, will be still a contact theory. So the next leading order still have this cutoff that you have to push to infinity. This is a perturbation. And doing perturbation theory is simple in many-body method, because you have the wave function that comes from the leading order and then apply just a very short range interaction in the Feynman-Golden rule for calculating first-order perturbation theory. That's pretty easy, and you can do that. It's not expensive. So this will make next leading order calculation much easier than before. And as I said, no changes in the theory. So the power counting will be the same. The leading order, you will lose information, I would say, about renormalizability, but the next leading order will recover them. And I think this is the news. This is the new part of this kind of theory, that you restore the power counting. And what you would expect, what you hope is that if for a certain range of the interaction, oxygen was breaking for alpha, when you decrease the interaction, the range of the interaction, when you increase the range of the interaction, so for example, this is half Fermi, the oxygen go back to be bound, and from that you can start to do perturbation theory and recover your theory. So when we try to work on this, we didn't want to start with nuclear physics. This will take just a couple of minutes more. But we started with atomic systems. Why atomic systems? So this is a good example why you want to work on interdisciplinary systems, because atomic systems have very similar properties, at least helium-4 in this case, as nuclear physics, but they are simpler in some cases. So they are simpler to be experimented, and we have many calculations. Helium's atoms are also bosons, so you have many less problem with spin isospin. So this is a perfect toy system to test your nuclear interaction. If everything works correctly, then you can go to nuclei and see if the numbers match the nuclei. But the first thing we want to do is to go to helium atoms, because we have a lot of calculation in effective field theory, and we can essentially check that our theory is correct. In particular, one thing that we want to check is, going back to oxygen, the range of the interaction cannot be too large, because if the range of the interaction, the auxiliary interaction that you have is too large, this cannot be corrected next to the linear order. So there should be some limit. And this is what we want to test here using atoms. And I will just give you an example. This is the last paper that we published. It's in publication right now. It's in printing right now, but you can find it in archive. And if you're watching on YouTube, probably this is already out. So here we calculate the 5-body energy. So those are 5 helium atoms, not 5 nucleons, 5 helium atoms that interact with a contact theory. And this is a leading order calculation which has a range, and the range is given by R bar, okay, tilde, sorry. And the next leading order have a cutoff, because this should become a contact interaction next to leading order. So you can see this, for example, just on the right, for each fake range that we choose for our theory, okay, we have different next to leading order cutoff, and here there is the energy of the 5-body system, and the cutoff variation is the blue band. Now, this light band here is the standard effective field theory, so the contact effective field theory at leading order plus the truncation error of the theory. This is the leading order. This is the next leading order. You see how this improves. The green line is the experimental value, or what we take as an experimental value. And we fit our theory on, and you see how much this improves. So this goes from here and here, and the error also becomes smaller. Now, when you choose, for example, one range for the 2-body, for example, here, you can see that you have a blue band. This is a cutoff variation for the next leading order, and then you extrapolate for the contact next to leading order. Of course, the leading order still have a range. Next to leading order becomes a contact, and you get the blue star. And you see that this blue star is inside the error band of the standard next to leading order. Actually, all these points inside the error band given by the blue band that you can estimate are inside the error band of the next leading order. Of course, the central value will coincide at a certain point, because when the range of the leading order becomes very small, it's like having a contact theory at leading and next to leading order. So here is naturally that they will coincide. Also for smaller leading order ranges, so for larger leading order ranges, you see that we get consistent results. And I would stress that those calculations are much easier than these calculations. So you just have a leading order, and then you have a perturbation theory that gives you this band. And numerically, this is much, much easier than just doing a lot of calculation for a lot of different cutoffs. So numerically, this is much better. One thing that you can say is that this way of doing the theory works pretty well. You can have a finite range at leading order, so you can improve your leading order and still get next to leading order correctly inside the error band of the theory. But then there is something that is extremely interesting. You see this pointed line? This is the range of the theory, is the range of the leading order that gives the correct effective range of the 2-body scattering of the theory. And you see what happened to the next leading order before this point. When the range of the interaction becomes larger, so you go on the left, this is the range to -1, becomes larger than this point, next leading order actually crazy, goes banana, cannot anymore correct what you are doing to the leading order one. And this looks to be quite a hard point. There is some takeaway of this. There is something to take home from this calculation, even if those are atoms. You can change your leading order of the theory, but be careful, because if, for example, you want to use a leading order that has a certain range, and then you want to be able to go back to the contact limit, the normal power counting, power control, and so on, you should be careful that the range of your leading order interaction cannot be larger than the physical range of your theory. And you see that if you go too much on the large side, then your theory starts to not converge anymore, and everything is bad. But you have some allowance, and you can improve your calculation. Now, we are working also in the nuclear case. Now that the atomic case taught us something, we went to, for example, this phase shift using energy-dependent delta shells, with a completely different interaction, and is in nucleon in system in which you have the leading order is the green one. Here is the non-improved theory. This is a paper that we are going to publish, I hope, very, very soon, with Manuel von Valderrama and Bira van Kolk. And you see that the leading order is what it is, and then the next leading order improves on that, and again, and 12 and so on. On the other hand, you have, when you have the improved theory, which is on the right, you see that already the leading order is actually on the top of the next to leading order one, and then the improvement, so how much is the convergence of your theory, is much faster. But on the other hand, you also see that the theories start to fail at the same point. So this improvement does not change the range of convergence of your theory. It just makes it to converge faster. And doing that, you also make your numerics easier. So to conclude everything, so what I wanted to tell you today is that theoretical nuclear physics is not something that has been already solved by many years. We still have interesting things to do or things to solve, and few of the which comes with the fact that we have some effective theory formulation that I would say become fancier and fancier to be used. That gives you a possibility to control the systematically improvement and error of your theory. But this effective field theories is not yet set on stone. So there is still some features like the renormalizability issue. So you want to have possibility to go to the contact limit, again, to have error control. But if you do that and you focus on that, you are actually giving up the fact that the leading order interaction, well-described physics, and you start to have instability problem. Namely, you want to have a way of stabilizing P-wave systems that a leading order, at least for Pioneer's effective field theory and the modified chiral effective field theory power counting, are not stable against the collapse in alpha particles and S-wave clusters. And what we propose is a new method to solve this instability problem, which is this improved action method that changes only the leading order of the theory, but not the theory itself. And essentially, this has been tested in bosonic systems, where it looks to work well and teaches us something on what are the freedom of doing this. Of course, this is not a new idea of using a finite range, but here you have really a codification and a theory, how much you can modify your leading order, what is your freedom, and how you restore power counting. So it's very important that you go to next leading order. Next leading order is still contact theory, so you don't modify the power counting itself. And this is a good way of having essentially easy way of dealing stability problem. You have still the properties of well-defined renormalizable power counting, and in the same time you have a softer leading order. This means that you also improve your capability in many-body methods, allowing you to go to bigger systems and increase the range of applicability of this application. So thanks a lot for your attention.